Okay, now we're back with an example problem to do, and in this example problem we've got basically a big pipe, and we're going to say that we've got some sort of internal pressure in there if this system is pressurized, and what we want to know is what is the normal stress and shearing stress, normal stress perpendicular to the weld, and the shearing stress parallel to the weld. Now to say what we're talking about there, you should know that this pipe, this particular type of pipe, is made by a weld that goes along like this. All right, and I'll show you a video here in a minute. But basically, it's a weld at like 30 degrees here, and the way that they make these things is particularly cool. So take a look at this video a minute. Here we go. And I'll skip to some parts here, but basically we have coils of steel like this that we're going to roll into these pipes, and we'll skip ahead a little bit to the system that does it. So basically it's rolled, those coils are rolled in a spiral pattern like this, and you weld the seam, and this is a particular type of welding called submerged arc welding. The arc of the weld is submerged underneath this flux, and basically it's a powder flux that helps the electrical conductivity of the material, and it helps with a number of other chemical properties of the steel and of the weld, and basically it also keeps splattering and other things down. So anyway, so submerged arc welding, SAW welding, and let me skip ahead a little bit more because there's a couple of shots here that show you a little bit more how the coil comes in and rolls up. So here you can see the coil coming in down here at the lower part of the shot, and it gets rolled up in these rollers so that you turn it into a pipe. Let's skip ahead a little bit more. Very cool. There's another shot of the outside with the coil coming in. Okay, so that is our example problem. Let's go back to it here, and we're told what the material is. We're told that we got a spiral seam. We're told up here at the top what the angle of that thing is. We're given the internal pressure. We're given the diameter here, and we're given the wall thickness. All right, and just to give you an idea of kind of how we're going to set this thing up, we basically say that we've got this pipe like this, and on that pipe, we've got a stress element, right? And we've got axial stress acting like this. We've got hoop stress acting like this. All right. So just like we have done in the past, where we have a sigma x and a sigma y, we have a sigma x and a sigma y, and it happens to be the axial and hoop stress. And in this case, we want to know what's going on a plane that is off at 30 degrees like that. Okay, so let's figure out what that axial stress and hoop stress is, and in order to do that, we're going to have to figure out what our internal radius is. All right, so to get sigma h and sigma a, we need little r. All right, so the internal radius is little r, and we're going to say that that's 1 meter. That's our outside diameter, and the wall thickness is 50 millimeters. So we're going to subtract 2 times 0.05 meters and divide that by 2. that's 0.45 meters. Right, that's our internal radius. So then if we compute the axial stress, that's going to be our internal pressure times R over 2 times T, and our internal pressure is 950,000 pascals. Our radius is 0.45 meters, and our wall thickness is 50 millimeters, so 0.05 meters. That's going to give us 4.275 megapascals if we do the math there. And our hoop stress is just PR over T, right? Which basically is the same thing we just had up above, except that we don't have the factor of 2 in there. So that's going to give us 8.55 megapascals. So let's make a stress element here. It's going to look like this. Sigma A is 4.275 megapascals. Our sigma H is 8.55 megapascals. And what we want is what's going on this plane right here. That's 30 degrees off that way. Whoops. So that means we're interested in theta equals 30 degrees. All right, so let's say that we're going to set up axes like this of x and y. Whoops. X and y like that, and we'll say what is happening at theta equals 30 degrees, which is the plane of that weld. So our sigma n is going to be sigma x times cosine theta squared plus sigma y times sine theta squared plus 2 times tau xy. Oh, why does it keep doing this? Two times tau xy times sine theta cosine theta. Let's put our numbers in there. Our sigma x in this case is 4.275 megapascals, and our angle is 30 degrees, and our sigma y in this case is 8.55 megapascals times sine squared of 30 degrees, and we have 0 shear stress. So that last term is 0. If we do that calculation there, we've got 5.34 megapascals, and that's the stress normal to the weld. All right. If we want the shear stress along the weld, we're going to need our other stress transformation equation, tau nt. That's going to look like negative sigma x minus sigma y times sine theta cosine theta. And we've got a tau xy times cosine squared theta minus sine squared theta. All right, and since again we don't have any shear stress on this stress element, so all we have left is the two normal stresses, sigma x and sigma y. So let's say we've got minus 4.275 minus 8.55, and then we've got sine of 30 degrees, cosine of 30 degrees, and that's going to give us 1.85 megapascals. And that's our shear stress parallel to the weld. All right, and that's the end of our example problem. And email me or let me know if you have any questions. Thanks.